Hello everyone, this is Andy Reza. Today we will continue with our theory of AI, and in this episode I will cover up A star. As you can see, the algorithm for A star is a bit involved. So let's take a look at it line by line. This is what you will find online everywhere. It's written in mathematical words. I will first look through that, then I will move on to a theory of how you can implement it inside programming. Now, at the start of the algorithm, you define two different containers, whatever you call them, lists, hash tables, whatever. These are open and closed, and at the start they are nothing. They are empty. Then, for the start point of your path, you put the g-score of that point to 0. You say that, hey, the parent for the start node is the start node, of course. Then by doing this, you'll add the start node inside the parent list. After that, you go inside the loop that says, hey, if the parent, if the open list still has something in itself, and this line will add start to open list, okay? To open. So while open list is not empty, do some stuff. First of all, make a variable called s and assign the very first item in the list. Now we immediately check if this item is our end point. If it's our goal, then we early exit here with finding the path, because up to this point we found the path. Otherwise, we add current node to the closed list. After that, we get the neighbors of this node that are visible to this node, and for each one of the nodes inside this second list, we call S prime. And for S prime, if it's not inside the closed list, then we check if it's not in the open list. Then first thing we do, we assign the g-score of this second node to be infinity. Then we assign the parent to be null. After that, we go inside a method that calls update vertex for s with this little node inside the neighbors list. So we repeat it for every node that is neighbor of this node, and we continue the while loop up on top. At the end, two things happen. One, either we found a node here, that is the goal, so we return early out of the loop, or if it comes to this bracket here, then it means that we didn't encounter the end goal, so we return with no path found. Now, this update vertex method, first we define a variable for g-score and we call it g-score old. We assign it to the g-score, we assign it with the g-score of the s prime that remember is a neighbor of the s. Then we go inside another method that is compute cost between the current node and its neighbor. After that, we say if the g cost of the neighbor is less than the g cost of old, and remember here first thing we done is that we assigned infinity. So the first time this is always true. Other than that, it may be true, maybe not true. Okay? So if that's the case, we check if the neighbor is in open list, then we remove it from open list. After that, we insert the new neighbor to the open list, and am I calling it correctly? Yeah. We again add this neighbor to the open list with a new calculated variable that is new g plus new h, and if you call it's f cost. Okay. Now the last method, that is compute cost, we say if the g-score of the current node plus the cost that we calculate between the nodes is less than the G-score of the neighbor, then we say first assign the current node as the parent of the neighbor node. Second, assign the current node's G-cost from plus this calculated G-cost to the new cost of the neighbor. Now, as you can tell, this mathematical way of presenting the algorithm can be a bit confusing. So, let's take a look at how we can implement it in programming. First, and I will call it another color, your open and closed. These two can be list, and in closed set I used hash table and I was successful. Okay, then what you would do is that first things first, you add, so one, add start to open list. The second time we go into the while loop that says if open dot count is greater than 0. While this loop is going on, next we say that if while this loop is going on, first things we do is assign a new variable calling current node. Okay, and to this guy we get the first element in open. Okay, and instantly here we remove it from open as a side node. Okay, then we say that if current node equals to the end node that we are targeting, then return the path. Otherwise, continue on. Now what we do, we define a new list that we call neighbor, and this is a new list of neighbors for current node. Okay, then we'll loop neighbors, and the very first thing we do inside this loop is that we say one if closed contains neighbor, then continue the loop. We have nothing to do. Otherwise, we calculate the cost to the neighbor from current node. Okay, after that we say if the cost is less than neighbor's current G-score, let me see if I'm doing it correct. Yep. Or the open set does not contain neighbor. Then we have stuff to do again. What we'll do is that we say neighbors gcost equals to the cost that we calculated, okay? After that, we say neighbors hcost equals to the new calculation of hcost. And here you can use distance between the two nodes as an example. After that, we say that neighbor's parent equals the current node. And then we check if not open set that contains neighbor we add neighbor to open set. Otherwise, we want to update the open set for current node, for neighbor node. And then we close out of every loop that we have. And this is the while loop, by the way. Okay. And at the end, we say, hey, path not found. Because we already are checking if the path found here, right on top. Okay. Now, the only thing here that needs to mention is this update the open set for neighbor. What is this guy? Well, depending on how you implement this system, if you use a heap map or if you use a list, you want to set your current node to this neighbor now and then get its neighbors, then continue on. Okay, so the thing that will happen is that at the end of this algorithm, we will get something like this. We will start from the start node, and this is our end node, and these are all the nodes in between. So 1, 2, 3, 4, 5, 6, 7, 8, and this continues on, okay? And like that, although there will be nodes above it, so like this and below it. Okay, so what we'll do is that at the start of the algorithm, first we add it to the open list, and then we go into a loop. We get these neighbors. For each one of them, we calculate the cost between these two, and we take a look at, hey, okay, which one of them has lower cost relative to the goal. So it will choose this neighbor and adds it to the and then says that, hey, this neighbor's parent is this node. Then we will add this guy to the open set, and we remove this guy from open set. So we continue evaluating this guy. It will return these nodes, And remember, now this guy is a neighbor to this guy. But now it's in closed set, so we don't need to evaluate him anymore. So we evaluate others. And by the evaluation, we find that this guy has the lowest cost. We assign the parent to him. And again, setting this guy into the closed list. So this guy is closed, this guy is closed. Then we get the neighbors for this one. We evaluate, we find this one. We assign the parent, we move this guy to the closed list, and we continue on till we reach to the point that we say, hey, the neighbor that I'm evaluating right now is the end node. So we assign the parent, and by doing that, we found our path. Okay? So this is the whole thing about the algorithm. Now remember, A star is not optimized. It's a very exhaustive search, and based on your complexity in the scene, it can evaluate lots of nodes in the scene. So for example, if you have a simple scene that has a start and an end, the path is just evaluating something like this. Very straightforward between the nodes till it gets to the end node. But if in between here we only add one single obstacle like this, okay, what will happen is that this guy will evaluate this node, this node, this node, and it will continue like it's going up to here. Okay, as soon as he hits here, he will go up and down at the same time. So it will evaluate all the nodes to this point, all the nodes to this point, and then this and this. And then he will continue on both directions. But as soon as he finds this guy, then he says, okay, I found the path. And the path is this. But that's for one obstacle. Now, if the scene becomes more complex, like the thing that we really have inside the real gaming situations, with tons of obstacles like this, this, and this. And if it's start here, I didn't mean to do, okay. If the start is here and the end is here, now the very first time he moves forward to that end, he may hit this wall. So he will continue on both directions. Moves on, then he will move from here to here. He moves from here to here and says, okay, I found two nodes. I will move from here to here, from here to here, and again from here to here, and from here to here, till he gets to this point and this point. And he will still continue on toward the goal when he hits this point. When he hits this point, then he moves down, he moves up, this guy moves to the left, this guy is moved to the right, he passes it on both directions, here and here, here and here, and he will continue on. This guy will continue on, this guy will continue on, And again, this guy will start moving up, moving down, moving up, moving down, left and right, toward the goal, toward the goal, toward the goal, and toward the goal, toward the goal, toward the goal. And remember, this is a long distance, so by the point this guy reaches here, all these others are evaluating themselves. Same for this guy. So when he is hitting here, he will go down, he will go up, then moves toward the direction, moves toward the direction, and the stuff repeats. So you can now imagine how many nodes will be evaluated. I would dare to say that, let me open it up and raise my brush size. Really big, thank you. I would dare to say that all these positions all of these will evaluate it, no matter what. So by all means, A star is not optimized. A star is very exhaustive depending on the complexity of your scene. Now, there are, but before I continue on, remember, A star is the parent of most of the newer algorithms. So whenever you see something like, not that, what I'm typing, what I'm writing, not typing, something like theta star, lazy theta star, D star, B star, and HPA star. All of these that has stars are one way or another being evaluated from A star. So if you want to move on, if you want to, for example, implement theta star or lazy theta star, that for games, or HPA star, these three on the left hand side are best for game environments. If you want to implement them, you first need to implement the A star. Understand the A star, make it work, understand the algorithm, and then and only then you can understand how to implement something like theta star. And let me zoom back a lot. Where I am now, okay. I think it's clean. Yeah. Well, for example, theta star says, okay, when I got to this point and I'm evaluating it to this point, I don't need these nodes between. I will directly bind this node to this one. And I'm very bad at painting, but in a direct line, Then when I evaluated this up to here, I will say, this is my path. Then this is my path, and this is my path, in this case. On the other side, okay, this is my path, continue on to this point. Then, for example, this is my path, and let's see, continue it to this point, for example, okay, then to this point. Whichever one of them is giving you the closer numbers. In this condition, for example, it will say, okay, this is my next path, this is my next path, this is my next path, and then continue on. Or This is my path. This is my path from here to here, then from here to here. So what theta star does, it does not make A star that much closer for exhaustiveness, but the path that he is returning is optimized. Although it would uh, optimize the algorithm for search again, because as soon as he finds these corners, he will not evaluate any other nodes in between. So in sort of the way, it reduces the number of pathfinding, for example, from here to here, number of nodes that is pathfinding on. But don't forget, it's actually theta star is a very little change in A star. Like you tweak 3 or 5 line of code and you get theta star. So if you want to understand how theta star is working, and on top of that how lazy theta star is working, you need to first understand A star. If this video was a bit fast in pace, well, there is always the option to go back and you know, pause the video when I'm going through this algorithm and watch it again and again and again. And I suggest you to watch this little video at least 3 or 4 times, especially when I'm starting to implement this pseudocode algorithm. The mathematical way, well, in my opinion, it's understandable, but for some new coders, it may be confusing. But this type of going on inside the list may be more understandable. So I suggest you to watch the video at least 3 times, then try to get your hand dirty first on A-star algorithm yourself. There are tutorials out there about implementing A-star in C# and Unity, but I suggest first try it yourself. See where you stuck, because be sure that you will be stuck one way or another, then watch video, because then this stuff will be implemented in your brain forever, and you will understand A-star to the full extension. And don't forget, actually A-star, the very first time that was made, was not for pathfinding. Interesting, isn't it? The very first time A-star was implemented was for solution not solution solving, but problem solving. Yeah. Interesting. And the way the guy was using A-star was that he had a problem. He would break this problem into as many lower solvable problems, smaller problems. Then he would break each one of them to smaller problems, and continuing on and on until he would get a tree, some sort of tree. And the thing that I'm sketching right now is exactly heap map. Okay, I will speak about heap map in another video maybe later on. But then he would say, okay, I know where is my solution, I know what I want to get, and this is the bigger problem. So now do A-star search inside this tree and see if the solution is contains anywhere inside this tree or not. If there is, then I know, for example, this is the solution I'm looking for, so this is the path to solve the problem. Or if it was here, then this is the path to solve the problem. So A star has many implementations, and believe me, A star alone by itself is still being used in AI, especially for solutions on problems. But the easiest way to understand it is starting for pathfinding. And that is why you see tons of videos out there in YouTube implementing A stars for pathfinding as their first try on A star. When you got this guy working, then the next problem would be to make your code so that the A star becomes generalized enough to be used for problem solving. And then you would say, okay, I have something to be used on real AI in real time. I had implemented that code, and me and David Stewart recorded chapter 1 on that. I had put the demo on the YouTube channel before this video, but it would be the sticky one till we get the chapter 2 done. And I'm showing you the result of exactly doing A star. And between 3,400 nodes, my pathfinding is 0 millisecond. So almost always. It's like 4,000 times on 0 millisecond, then 2,000 times on 1 millisecond, because I'm recording the video at the same time. So if you reach this point, that's when you can say, okay, my A star algorithm is robust enough so that I can now sit down and generalize this guy. And that's when you want to move on to something like theta star. Although in next video I will cover theta star's algorithm, and after that I will cover lazy theta star's algorithm, because you know I'm just recording video tutorials on theory behind AI. So but in reality, when you want to move from A star to theta star is when first you made pathfinding like this, and then you made A star generalized enough, or at least get to this point and then try to implement theta star on this point. And when you made your theta star work, that's when you want to go into lazy theta star. So one thing I forgot to mention in previous episodes, something about breadth first search and its parent, that was deep first search, that I didn't mention at all. And then greedy best search. Believe it or not, and then A star. All these guys, one way or another, are still used in AI, even these days. So none of them are useless. Now, this one that I didn't mention, deep first search, well, you remember the breadth first search? There is very little difference between breadth first search and greedy first search. Sorry, deep first search. In breadth first search, we first get this level done, then we finish this level, then we finish this level, and then the last level. On the other hand, in deep first search, we first take a look at the first branch, then the second branch, then to this guy, to here, and this branch, then this branch. Then we will move to the second level of problems and see if we can solve it. So if I want to sketch with arrows, and sketch with arrows, buddy, this will be 1, this will be 2, this will be 3, this will be 4, this will be 5, this will be 6, this will be 7, then this will be 8, this will be 9, this will be 10, then 11 and 12. Okay, now this is deep first search compared to breadth first search. Let me just mimic my algorithm again. And this guy has 2, this guy has 2, this guy has 2, but each one of them has 1. Okay, now in breadth first search, this is the way. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. Okay, so you get the difference between these two. This is deep, this is breadth first search. This was developed first by mathematical guys, then it evaluated to breadth first search, and of course breadth first search became greedy best first search, and greedy best first search became A star. So this is still being used. You may ask where it's being used. Behavior trees. And this is still being used. Where? Again, behavior trees. Depending on the node that you put on top on the behavior tree, you would force him to do this guy or do this guy. Okay? For example, in this case, I think, what was the name? Well, I know this is sequence. It's sequential. So, well, it will evaluate this node, then it will evaluate this node. And if both of them succeeded, then this guy will be returned succeeded. This guy, for time being, I forgot the name. This is when if any one of the children's anywhere returns success, exactly this guy immediately returns success. I forgot the name of this guy right now. Sequence and blah, I forgot. I need to sit back and think like 3 minutes to remember this guy now. But anyway, so in reality, these things are still very valuable because behavior trees are very great way of making advanced AIs. Don't forget that. Okay? So I'm still trying to remember this guy's name. It's not coming to my mind right now, top of my head. Anyway, so these two still are valuable. And don't forget, greedy best search is what is making A star A star. And A star is what making theta star. And theta star is what making lazy theta star. And again, A star is what making HP A star. And all these algorithms, all 4 of them, are still being used in games. Exhaustively, they are used in games. So sit down, watch the video time and time again, and try to implement A star first. If you have any questions, my weblog is unityai.net. I constantly post there. I constantly post my thoughts, my experience, other stuff that may interest you. So visit my website, and if you find any post that you may have a question, comment there. If you like any post, again, comment there. And if you like this video, please use that thumbs up and please subscribe. That will help both of them, help me a lot. Especially when you put thumbs up, I know that it became useful for some guy out there and it motivates me. That's what keeps me going on. Anyway, have fun everybody. Till next episode that I will cover Theta Star. Have fun. Bye bye.